Hi there. Previously, we saw that the derivative of a function f at a number a is given by f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. And we saw where that came from and what that means. But instead of taking a to be some constant, we can let a vary by replacing it with the variable x. And so we can write f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Now, this expression here has two variables in it, x and h. But remember, we're taking the limit as h goes to 0. So in the end, whatever we end up with, h is going to vanish, and this is going to be an expression that only has x in it. And in fact, we can regard this as a function of x. So we can look at the derivative of a function as another function itself. So this is the derivative of f as a function. So we're no longer going to consider the derivative to just be a number that we look at one point or another point. We're going to consider the derivative as its own function. This is one of the two most important ideas in calculus. The other one is the integral, something that you will look at later in the semester. But it's so important. This new function is directly related to the original function. It can be interpreted as the slope of the tangent line to the graph of the original function. It can be interpreted as instantaneous rate of change. It can be interpreted as instantaneous velocity. There's so many uses of this, and so we really want to learn how to calculate derivatives of functions more quickly and more easily. We want to see what the derivatives are of all the most common functions that we'll look at. And we want to get really comfortable looking at these graphs and comparing them. So what I want to do is I want to look at the graph of a function, and I want us to figure out, without doing any calculations, what the graph of the derivative is going to look like. So let's look at an example. Bing! I kind of wish I had a sound effect for whenever I had a graph just magically pop out of nowhere instantaneously, but we don't, so I'll just go bing. But anyways, let's look at this graph. Here we have the graph of a function. We don't know what the equation of the function is. We're just given the graph of the function. And I want us to draw a graph of what the derivative is going to look like. So I'm going to draw some axes for us, and then let's figure this out. So one of the things we know is that whenever we have a horizontal tangent line, we know that the slope of a horizontal line is 0. So at these 3 points, the derivative is going to have to be equal to 0. So we know that at this first point and the second point and the third point, A, B, and C, the derivative is going to be 0 in those positions. Now, let's look and see what's happening in the intervals between these. If we look at what's happening between A and B, we can see that anywhere in here, the function is increasing, which means the slope of the tangent line is positive. So we know that between these 2 points, the slope, or the derivative, is going to be positive. It looks like right in the middle is where it gets the steepest. And I would say the slope there looks to be about 1 or so. So if we wanted to label our y-axis here, 1 and 2, the maximum slope we get there is 1. So it looks like the derivative is going to be something like this. It's increasing, it hits the maximum 1, and then it goes back down to 0. Now, if we want to look between B and C, The function is decreasing. That means the slope of the tangent lines are going to be negative, and so that means the derivative is going to be negative. So because the derivative is going to be negative, we know that we're going to be down there. And then as we move to the right, from C to P and onward, the function is increasing, which means the slopes of the tangent lines are all going to be positive, which means the derivative is going to be positive. We're actually given a value. We're told here when x is 5, looks like the slope of the tangent line is 3/2, which means the derivative is going to be 3/2. So at this point, we've got 3/2. And so our curve is going to go up here. And yeah, not the nicest curve in the world. I've done better before, but it is what it is. And then also we have one more area over here to the left of A. This function is always decreasing, which means the slope is always negative, which means the derivative is always negative. So we're going to be down here on that side. So again, not the nicest sketch in the world, but we can see where the derivative is going to be positive, where it's going to be negative. We can see that it's going to be 0 whenever we have a horizontal tangent line. So we can get an idea of what the graph of the derivative will look like based on the graph of the original function. Now, I want to do one example where we were given a function and we take the derivative of that function and then we compare the graphs, but I'm kind of running out of space here and this video is already 6 minutes. So I'm going to stop this and I'm going to switch to another video so we can do that with a clean slate.